Okay, we're back to talk about some important features of waves. The one that, and a lot of these you've probably heard of from math classes, because you talk about these in math class for sine waves. And we did talk about them all last year, but just as a refresher, we're going to start with amplitude. And the amplitude is very simply the height of the wave from what I'll call, I guess, the equilibrium point, the midpoint of the wave, mid-height, to either the crest, or you can also measure to the trough. So over here I'm going to draw a nice example of a wave, and we're going to keep referring back to that as we go. So here's our wave. Okay, there's our nice looking wave. Now the amplitude would be this. Let's see here. I need to make this one a little taller. There we go. The amplitude is this, the height from the midpoint of the wave, or the mid-height, to the crest. So that's the amplitude. And for waves, what the amplitude corresponds to, it corresponds to the intensity of a wave. And that's not really a word we've talked about in the past, and we're not going to talk about it much now. The intensity basically means things like, if we're talking about a sound wave, we're talking about something that is a very loud sound, that's a very intense sound. If we're talking about light waves, we're talking about very bright lights. That's what intensity means. Okay? And the intensity corresponds to that amplitude. Next thing we're going to talk about is the wavelength, and I'll get to labeling this in just a second, but before I go and label this, we're going to just define it. The wavelength is the length in space of one complete wave cycle. Okay, the length and space of one complete wave cycle. I'm going to put that on there in a second, but before I do that, I want to talk about frequency, and also one that's not written on here, which is the period. And we defined frequency and period last time, in the last unit, for simple harmonic motion. But it would not be a bad thing for us to define it again. You know, make sure and check to make sure your definitions of these are correct. The frequency of a wave is how many complete wave cycles happen per second. The unit of that is hertz, as you remember. For sound waves, the frequency determines the pitch or the note or the tone. Okay, basically how high the note is, if you're musically inclined, determines pitch. Light frequency, as we talked about as I mentioned on the last video, determines the type of wave. Or, if we're talking about visible light, the color. The frequency determines the color. Okay? So that's frequency. And I do want to put on here that frequency is the inverse of period. Inverse of period, and as we know, the period is the time duration of one complete wave cycle. And since frequency and period are inverses, we can write that as F equals 1 over T, or T, capital T for period, equals 1 over F. Okay, so now I'm going to go back and define on the picture what wavelength or period is. If I label this, some of you would tell me that that's the wavelength, some of you would tell me that's the period, and the correct answer is you can both be right under certain circumstances. This segment of a wave could represent the wavelength if we are measuring on our x-axis in distance units, such as meters. It would show us the physical length of one wave. So imagine this is like literally like you took you had a string vibrating up and down or oscillating up and down, and you took a picture of it with a camera. And then you measured the distance, you had a ruler in the frame, and you measured the distance between peaks. That would be measuring the wavelength. So this is like if this is a physical snapshot of the wave, if we're measuring distance on the x-axis, this distance can be a wavelength, the length and space of one complete wave cycle. We could also say that the distance between here and here is a wavelength. We could even say from this midpoint when the wave is going up as we go to the right, to this midpoint as the wave's going up. Just make sure you don't say this is a wavelength, because that is not true. It has to be one complete wave cycle. However, if instead this is not a picture of the wave and this x-axis isn't measured in meters but in seconds, such as if we're measuring the, let's say we're measuring the displacement of one little piece of wave. So this shows that the wave element starts at the equilibrium spot, at the mid-height spot, goes up and then goes down, then comes back to its original spot and does the same thing here. In here, what that would be measuring, if we are measuring this in terms of seconds, if this is a position versus time graph for a point on a wave, then this length determines the period. Okay? So the period can be determined if this x-axis is measured in seconds. If it's measured instead in meters, then that shows us a wavelength. So you have to read the graph. I've been saying it all year. I've been trying to stress it. You have to know what information the graph is telling you. Is the x-axis in meters? Is it in seconds? Okay? Knowing that will help you determine what information you can get from the graph, whether it's wavelength information or period information. Okay? All right, let's keep moving. So we've got amplitude, wavelength, frequency, and period. Now we're going to talk a little bit about speed. The most important thing for the speed of a wave is that no matter what type of wave it is, the speed is constant for a given material or medium. Material and medium really mean the same thing. Okay? The speed does not change if the wave does not move into a different medium. That doesn't matter if it's a sound wave, doesn't matter if it's a light wave, doesn't matter if it's a wave on a string. The speed will always remain the same as long as the material the wave is traveling through, or the lack of it, remains the same. For sound, the speed of sound in air is approximately 340 meters per second. It does vary slightly with the air temperature, and if it moves into different materials, then it can change. For sound waves, the wave itself will increase in speed for denser materials or warmer air. And that has to do with the fact that sound waves are longitudinal. Longitudinal waves happen because the different parts of the wave, the different wave elements literally interact with each other. They kind of knock into one another, okay? And that propagates the wave. If you have a denser material, you have particles that are more tightly packed. That allows the wave to progress faster. If you have warmer air, those air particles can move around faster. That allows the wave to progress faster. Okay, so for denser materials or warmer air, the speed of sound will go up. So for instance, in water, even though when you try and listen to someone underwater it sounds all distorted, the sound is actually moving faster than it does in air. The speed of light, on the other hand, a light wave, is approximately 3 times 10 to the 8th meters per second. That's 300 million meters per second, I believe, if I got my math right, in a vacuum. And it's very, very close to that in air. It's just barely lower than that, so it's essentially the same thing. And for light, the opposite happens. The speed of light goes down for denser materials. Okay? So we have the speed of sound is 340 meters per second in air. The speed of light is 3 times 10 to the 8th meters per second in the air. Now, the last few variables that we talked about, speed, frequency, and wavelength, have a relationship, and that relationship is very important. We know that wavelength is measured in meters. We know that frequency is measured in hertz, and a hertz is just 1 per second. And we know that speed is measured in meters per second. So if we kind of combine all of those, we can see how this relationship should work. If speed is in meters per second, and we also have a variable that's in meters and one that's in 1 over seconds, what happens if we take the meter and we multiply it by 1 over seconds? M times 1 over s should give us m over s, and that leads us to the relationship of v, the speed, equals the frequency multiplied by the wavelength. Remember, this symbol is lambda. That's the symbol for wavelength. Okay? So the speed of a wave, of any wave, is equal to the frequency multiplied by the wavelength. That's subject to some rules. And one of the rules we've kind of already mentioned. So for a wave in a given medium, always remember that v, the speed, is constant. If the frequency goes up, if you have a higher frequency wave passing through that material, then the wavelength goes down, but the speed stays the same unless the medium changes, unless the material the wave is traveling through changes. Okay? So if you have, it doesn't matter if you have tons and tons of different waves passing through the same material. They can all have different frequencies. They will all have different wavelengths. Since it's the same material and the same type of wave, like let's say all sound waves. Obviously sound waves and light waves don't have to travel the same speed in a certain material. If you have 100 different light waves traveling through some material, the frequencies can all be different. The wavelengths can all be different. The speed must be the same for each. In another situation, for a single wave traveling between different media, f, the frequency, is constant. Upon changing media, media is just the plural of medium, the velocity and the wavelength change, but the frequency stays the same. Okay? So if you've already created a wave, and that wave is traveling between different media, different materials, the frequency will not change. The frequency has nothing to do with the media. Frequency has to do with how the wave itself was created. Once the wave is created, you can't change that frequency. Okay? So once that frequency is created, it stays there until the wave dissipates or dies out. As it changes media, the speed will change, and if frequency stays the same and the speed changes, that means the wavelength has to change. But the frequency will remain the same as the wave moves to different materials. So for instance, if you have a sound wave that starts off in air and then goes into water, the speed will change, the speed will increase, the wavelength will increase, but the frequency, the tone of that wave will remain the same. Okay? Let's test this out. Let's do a few calculations before we move on to our last video with speed and frequency and wavelength. Okay, so our first example. Let's say the speed of sound in air is about 340 meters per second. What is the wavelength of a musical note that oscillates at 440 hertz? So that would be the frequency. We're given the speed. We're just looking for the wavelength. That's a Regents question. That's extremely straightforward. The speed is 340 meters per second. The frequency is 440 hertz. We are just solving for the wavelength. And getting out my calculator, the wavelength becomes about 0.77 meters. Okay, a little shorter than a meter. Okay, so what if the frequency of the above sound doubles to 880 hertz? Let's say we have a different wave. The frequency is twice as much as it was before. What other changes can occur in this wave? Well, let's do some reasoning before we do the math, and then we can check our math. If the frequency doubles, we weren't told anything about what happens to the media, the material. So we're going to assume it stays in the same material. And since we're assuming it stays in the same material, that must mean that the speed remains the same. So since same medium, v remains the same. Well, if v remains the same and f goes up, that means that in order to keep v being the same, the wavelength has to go down, because the left-hand side still has to be equal to the right-hand side. The left-hand side didn't change. One of the factors on the right-hand side went up. If this stayed the same, then that would mean that these two sides are not equal anymore. If this stayed the same, this went up, and this stayed the same, then this side would then be greater than this side. So this can't stay the same. It can't go up, because then this would really be greater than this side. The wavelength must go down to compensate for f going up. And since we know that f goes up, it doubles, that means that the wavelength has to halve, and then those factors of change will cancel out. 2 times a half is just 1. This side, the product here, will remain the same. The wavelength is halved. And then just to prove this, we can do the calculation. V equals f times lambda. The speed is still 340 meters per second. The frequency is now 880 hertz. We solve for the wavelength, and we get 0.39 or so. And with some effects due to rounding, we see that this is exactly 1/2 of the original, because if I multiply this by 2, I basically get the same thing that I got in the original. Now, last example, what if instead that 880 hertz wave that we just created enters a new medium, such as a wave in air entering water? Well, since the wave has already been created, it's just entering a new medium, the creation of the wave affects the frequency. The frequency has nothing to do with the media that it enters. So the frequency is going to stay the same. The wave frequency has already been created. The number of oscillations that happen is set. That's not changing. Stays the same. Okay. Let's see here. We're dealing with a sound wave, so that means that the velocity goes up because sound travels faster in water than air. And it's going into water, so the speed's going to increase. And the wavelength increases because, here's our equation, if the frequency remains the same, but the speed goes up, the left-hand side has gone up, this variable on the right-hand side stayed the same. How do we make the total on the right-hand side go up? We have to increase the wavelength. So the wavelength increases. Okay? If we had actual numbers for what the speed of sound in water is, and you can look that up, it's pretty easy to find, then you could tell exactly what the new wavelength would be. When we come back, we'll look at 3 different phenomena, and then we'll be done with our basic wave stuff, and we'll move on to standing waves.